And finally, NASA on Tuesday said that it has found a heartbeat signal from the Voyager.
When that blast wave reached Voyager, it caused the plasma around Voyager to vibrate or oscillate in a certain particular tone.
Far beyond the planets where sunlight fades into a cold and dim glow, Voyager 1 drifts in the vast ocean between the stars. For decades, it has traveled through regions of space that no human-made object has ever reached, carrying its instruments into realms that exist outside the protective bubble of the sun's influence. Launched in 1977, it has long since left the planets behind, crossed the outermost boundaries of the heliosphere, and entered interstellar space. The spacecraft has endured cosmic rays, the relentless pull of deep space, and the sheer emptiness that would silence most machines. Yet even after more than 4 decades, it continues to send back signals, faint whispers across billions of kilometers, that still carry surprises no one thought possible. Before we start, smash the like and subscribe buttons for more updates. Recently, an unexpected reading from its aging scientific instruments sent ripples through the astrophysics community. Voyager 1 detected an anomaly in the interstellar plasma environment that defied current understanding. This was not a mere fluctuation or an easily explainable spike in data. It was something unprecedented, an energy signature unlike anything previously observed in the thin haze of particles beyond the heliosphere. In a place where space is thought to be stable, calm, and predictable on human timescales, the spacecraft found evidence of dynamic activity, waves or disturbances moving through the interstellar medium at intensities far beyond what models had predicted. For decades, scientists believed that once Voyager 1 passed into interstellar space, it would encounter a relatively uniform environment. The solar wind would be behind it, and the influence of nearby stars would be subtle, spread thin over enormous distances. The plasma, the sparse soup of electrons and ions between the stars, was thought to flow almost imperceptibly, with only occasional ripples from distant supernova remnants or slow-moving shock waves. Yet the data revealed something more energetic and complex. The readings suggested that Voyager 1 had stumbled upon a vast region where plasma density and energy were behaving in ways that current interstellar physics cannot fully account for. What makes this discovery so extraordinary is its location. Voyager 1 is over 150 astronomical units from Earth, more than 22 billion kilometers away, well outside the magnetic influence of the Sun. The disturbances it measured could not have originated from solar activity in any conventional sense. The distance is simply too great for the Sun's wind to create such strong effects. This raises profound questions about what is happening in the dark expanse between the stars. Are there massive unseen shock waves sweeping through interstellar space? Could there be entirely new processes shaping the structure of our galactic neighborhood? The possibilities are as unsettling as they are exciting. The instruments on Voyager 1 are simple compared to the advanced technology aboard modern probes, yet their reliability has allowed them to outlive every expectation. The plasma wave subsystem in particular has been crucial in detecting subtle changes in particle density and electromagnetic activity. It was this system that picked up the strange signals, a persistent, high-frequency oscillation in the surrounding plasma, sustained over months rather than fleeting moments. Such a continuous event in such a remote location challenges the belief that the interstellar medium is static on short timescales. It hints at a cosmos far more dynamic than imagined, where vast unseen currents and waves pulse through the darkness. One of the most striking implications is that Voyager the 1st of May have encountered a phenomenon linked to galactic-scale processes. In interstellar space, the primary drivers of energy and motion are thought to be supernova explosions, stellar winds from massive stars, and the slow drift of material through the galactic disk. These forces operate over millions of years and across unimaginable distances. To detect something significant over just a human-scale time span suggests an event either unusually large or unusually close. If such disturbances are common, they could play a key role in distributing matter and energy across the galaxy, influencing star formation and perhaps even the conditions for planetary systems like our own to emerge. There is also the possibility that Voyager 1 has crossed a boundary in the interstellar medium, moving from one region of space into another with different properties. The galaxy is not uniform. It is filled with clouds, voids, and filaments of gas and dust, some denser and more turbulent than others. If the spacecraft has entered a new environment, it might be experiencing the shock front or transition zone where two such regions meet. Such boundaries could act like cosmic weather fronts, generating turbulence, magnetic reconnection events, or particle acceleration on a massive scale. Understanding these structures would not only deepen knowledge of the interstellar medium, but also offer insight into how cosmic rays, high-energy particles that bombard planets, are produced and distributed. Voyager 1's data also challenges the assumption that interstellar space is an almost perfect vacuum in terms of sensory experience. The region the spacecraft traverses is unimaginably empty compared to Earth's atmosphere, yet it is not devoid of structure. The plasma behaves like a tenuous fluid, capable of carrying waves, oscillations, and pressure variations across light years. The discovery suggests that these waves may be more common and more powerful than previously believed, carrying the fingerprints of distant cosmic events. Each oscillation is like a message from across the galaxy, encoded in the ripples of charged particles. The implications for astrophysics are immense. If the interstellar medium is more active than models predict, then the life cycle of matter in the galaxy may be far more dynamic. Energy could be redistributed faster and more efficiently, with consequences for how interstellar clouds evolve and how stars form within them. On a more immediate scale, these findings could influence how scientists design future probes to withstand the hazards of interstellar travel. Stronger than expected plasma waves might affect spacecraft communications, power systems, or even their trajectories in subtle ways. A probe crossing such regions might encounter electrical discharges or high-energy particle bombardments capable of damaging sensitive electronics. Equally intriguing is the role such disturbances might play in shaping the heliosphere itself. The bubble of solar wind that surrounds our solar system is not a rigid shell. It flexes, ripples, and breathes in response to pressures from the interstellar medium outside. If Voyager 1 has found evidence of stronger external forces, it suggests that the heliosphere is far more sensitive to galactic weather than once assumed. Over millennia, these pressures could subtly alter the size and shape of the bubble, changing how well it shields planets from cosmic radiation. The discovery also reignites discussions about the unknown hazards of deep space travel for crewed missions. While human journeys beyond the heliosphere remain a distant dream, these findings highlight that interstellar space may not be the serene emptiness once imagined. It is a realm of invisible storms, where energy flows and particle streams can shift unpredictably. Any future explorers would need protection not only from radiation, but from electromagnetic phenomena, whose strength and frequency are only beginning to be understood. Beyond the technical and scientific implications, there is a profound sense of wonder in the idea that a spacecraft launched in the 1970s is still capable of making groundbreaking discoveries. Voyager 1 was built in an era before personal computers, before the internet, before modern digital communications. Yet its instruments, running on power from a slowly decaying nuclear generator, have outlasted generations of Earth-bound technology. Each bit of data it sends back is a triumph over time and distance, a reminder that curiosity can endure far longer than anyone dares to plan for. What this detection ultimately means is still open to interpretation. The data points to a phenomenon that fits no simple category, too sustained to be a passing shockwave, too localized in its readings to be dismissed as background noise, and too intense to align with older models of the interstellar medium. It invites questions about how many other regions like this exist, and whether they form a hidden network of energetic zones threading through the galaxy. Perhaps the space between stars is not an empty void at all, but a living, shifting expanse whose unseen motions quietly shape the environments where stars and planets are born. The challenge now is that Voyager 1 can only measure what its limited instruments allow. It cannot turn and look for a source, nor can it sample particles directly in the way modern missions might. The spacecraft's aging systems mean that each transmission takes hours to send and days to analyze, and its position cannot be altered to investigate the phenomenon more directly. Still, its journey offers something no other mission has: direct, real-time measurements from a place where human eyes have never looked. Even with its modest tools, it continues to deliver surprises that force scientists to rethink long-held assumptions. The sheer persistence of this plasma activity hints at processes operating on scales that dwarf the solar system. If it is the echo of a supernova's blast wave, then Voyager 1 is hearing the aftershock of a star's death from possibly hundreds of light years away. If it is a boundary region between interstellar clouds, then the spacecraft is tasting the edges of vast, unseen structures that stretch across multiple star systems. Each interpretation adds depth to the picture of our galactic neighborhood, turning the idea of interstellar space from a featureless void into a complex, active frontier. It is worth noting that the interstellar medium is shaped not just by ancient cataclysms, but also by the slow, steady influence of magnetic fields. These invisible lines of force thread through space, guiding the motion of charged particles and influencing the shape of gas clouds. If Voyager 1 has entered a region of unusually strong or tangled magnetic fields, that could explain the persistent plasma oscillations. Such a scenario would suggest that magnetic turbulence plays a far greater role in shaping interstellar environments than once thought, potentially affecting everything from the movement of dust grains to the acceleration of cosmic rays. The spacecraft's detection also hints at a subtle interconnectedness in the galaxy. The wave patterns it senses might be the combined result of multiple distant events: stellar winds from one direction, a shockwave from another, magnetic compression from yet another. Interstellar space, in this view, becomes a tapestry woven from countless overlapping influences, each adding to the texture of the environment through which Voyager 1 drifts. This complexity mirrors the interconnected systems on Earth, where oceans, atmosphere, and geology interact in ways that create dynamic, ever-changing conditions. The idea that there are weather systems in interstellar space has profound implications for astronomy. If these disturbances can be mapped, they might serve as markers of past and present events in the galaxy. Much like tree rings reveal a record of seasonal changes on Earth. They could show where supernovae have exploded, where clouds of gas are compressing into stars, or where magnetic fields are being twisted and reshaped. For future probes, such maps could be as important as star charts, guiding them through regions of relative calm or steering them towards scientifically rich areas. At its heart, this discovery is a reminder that the universe is never truly still. Even in the loneliest, coldest stretches between the stars, there are currents, flows, and pulses. Energy moves, matter shifts, and the traces of ancient cosmic events ripple outward for centuries or millennia. Voyager 1, small and alone, has touched one of these ripples, and in doing so, has opened a new chapter in humanity's understanding of the galaxy. It proves that the frontier is not a line to be crossed, but a living, breathing expanse that stretches endlessly outward. As the spacecraft continues its silent journey, the data it gathers will be studied and debated for years. The signal it found will be dissected in countless ways, compared to models and tested against simulations. Whether it marks a unique event or the first observation of a widespread phenomenon, it has already changed the way scientists think about interstellar space. It has replaced the image of a static, inert void with that of an active, restless sea whose movements can only be glimpsed through the patient work of explorers like Voyager 1. The vastness around Voyager 1 is almost unimaginable. Yet even in that emptiness, there are patterns and structures that subtly shape its path. Each new transmission from the spacecraft brings with it the possibility of revealing something entirely unexpected. The recent detection of this unexplained plasma phenomenon is not just another line in a long record of measurements. It is an event that forces the scientific imagination to stretch beyond comfortable theories. It demands new thinking about how energy and matter behave on scales too vast to recreate in laboratories, or even model with complete certainty. The raw data, when first analyzed, seemed almost impossible given what was understood about the interstellar medium. The wave intensity, its duration, and its consistency over such a span of time contradicted the notion that Voyager 1 was passing through a quiescent, unchanging environment. Even the most seasoned researchers who have worked with decades of Voyager telemetry felt the weight of its implications. To them, this was not simply a signal. It was the footprint of something powerful, moving silently through the darkness. Interstellar space has long been described as thin and diffuse, with only a few atoms per cubic centimeter, and with energy exchanges happening at a languid pace. But these readings suggested a more volatile environment. It was as though Voyager 1 had found itself on the edge of an unseen tide, its instruments registering the pull of forces that, until now, were thought to be muted in such remote regions. Plasma waves of this nature require a driver, something to inject energy into the medium and sustain its motion. Identifying that driver is the first puzzle. One possibility is that the disturbance comes from faraway stellar activity. Stars across the galaxy shed streams of charged particles in their winds, and when these winds collide with the ambient medium or with each other, shock fronts can form. These fronts can travel for hundreds of light years, their energy slowly dissipating but sometimes encountering denser patches of interstellar material where the energy becomes concentrated and amplified. Voyager the 1st of May have passed through one of these regions, sensing the lingering echoes of such a colossal interaction. If that is the case, then the scale of what it has encountered is staggering. The energy to produce a detectable wave at such a great distance must have been immense. It would suggest that the interstellar medium is not as homogeneous as once assumed, but instead a patchwork of pockets. Some quiet, some turbulent, all shaped by the long history of nearby stellar births and deaths. These pockets could serve as archives of cosmic history, holding clues about the timing and location of ancient stellar events. Another possible source of the phenomenon lies in the realm of cosmic magnetism. Magnetic fields in interstellar space are notoriously difficult to measure, but they are known to exert control over the movement of charged particles. In certain conditions, magnetic lines of force can snap and reconnect, releasing bursts of energy. This process, magnetic reconnection, is well studied in the Sun's atmosphere and in planetary magnetospheres, but in interstellar space, it could occur on scales far beyond those in our solar system. If Voyager 1 has stumbled into a region where such reconnection is happening, it might explain the persistent, high-intensity plasma oscillations. Understanding such a process in the interstellar context would be revolutionary. It could provide missing pieces to the puzzle of how cosmic rays, the high-energy particles that constantly strike Earth, gain their immense speeds. If reconnection events in interstellar space are frequent and widespread, they could be a significant contributor to the acceleration of these particles, adding a new dimension to models of galactic energy transport. The sheer remoteness of Voyager 1's location makes the implications even more profound. Every reading is a sample from a realm utterly inaccessible by any other means. Telescopes can detect light and other electromagnetic signals from interstellar space, but they do so by integrating vast regions together, blending them into an averaged picture. Voyager's data, in contrast, is a point measurement, specific, localized, and grounded in physical contact with the environment. It is as though, instead of studying an ocean from space, we have dipped a single finger into it, feeling the actual texture of the water. For decades, scientists have dreamed of interstellar probes with advanced sensors capable of mapping these vast and distant regions in detail. Yet even with its comparatively primitive technology, Voyager 1 is giving a taste of the surprises such missions might find. The plasma disturbance it has encountered is a reminder that the road beyond the solar system is not a straight path through an inert void, but a journey through an active, ever-changing galactic landscape. These findings also force a reconsideration of the boundaries that define our solar system's place in the galaxy. The heliosphere, inflated by the solar wind, forms a kind of protective cocoon around the sun and planets. Outside that cocoon, the galaxy's own weather takes over. Voyager 1's latest readings suggest that this galactic weather is more variable and possibly more intense than we thought. If the heliosphere is constantly being buffeted and reshaped by such forces, then its protective qualities may ebb and flow over cosmic timescales, influencing the conditions on planets inside. Such changes could, in theory, affect climate stability on long timescales, altering how much cosmic radiation reaches planetary surfaces. While the timescales involved would be far beyond human history, they could be relevant to the study of planetary habitability in other star systems. If our galaxy's interstellar weather is as dynamic as these readings imply, then planets orbiting stars with smaller or weaker protective bubbles might experience significant variations in radiation exposure with direct implications for life. In this sense, Voyager 1 is not only exploring space for curiosity's sake, It is building the foundation for understanding the galactic context in which all planetary systems exist. Its detection of a large-scale sustained disturbance is like finding a previously invisible force that may influence the evolution of entire solar systems. It elevates the interstellar medium from being a mere background into an active player in the theater of cosmic events. There is also a philosophical weight to the discovery. Humanity has always sought to chart its surroundings, to understand the forces at work in its environment. With Voyager 1, that drive has reached a point far beyond any coastline, mountain range, or planetary horizon. We are now mapping the unseen tides of a sea that extends between the stars themselves. The fact that this exploration is being done by a craft built more than 40 years ago is a testament to the endurance of both human engineering and human curiosity. The data that brought this phenomenon to light was faint, barely distinguishable from the background noise. It had to be carefully filtered, processed, and compared against years of earlier measurements to confirm that it was real. This meticulous work underscores just how challenging it is to conduct science at such extreme distances. Every bit of information from Voyager 1 travels for more than 20 hours before it reaches Earth, carried by a signal so weak it would be lost without the largest and most sensitive antennas ever built. The discovery also points to the need for continued investment in deep space communication infrastructure. Without the capacity to detect and interpret such faint signals, this event might have gone unnoticed, buried in the noise. Future missions designed to travel even farther will rely on an even more robust network to return their findings. In that sense, Voyager 1's detection serves as a warning. The most extraordinary discoveries may be hidden in the weakest of signals, and without the patience and technology to find them, they will remain unknown. Some researchers have speculated that the disturbance could be tied to the boundaries of a nearby interstellar cloud. The Sun itself is moving through the galaxy at considerable speed, and it occasionally passes from one region of interstellar space into another, each with its own density, temperature, and magnetic characteristics. If Voyager 1 is sampling the edge of such a transition, it could be providing a rare glimpse into how these clouds interact. The dynamics at such boundaries could be far more violent than the calm interiors, with shock fronts, turbulence, and magnetic shear all contributing to complex plasma behavior. Studying such boundaries directly could provide valuable insights into the structure of the galaxy's spiral arms and the processes that shape them. The Sun's journey through these environments is an ongoing story, one that stretches back billions of years and will continue for billions more. Each crossing may leave subtle imprints on the solar system, influencing everything from cosmic ray flux to the chemistry of the outer planets. Voyager 1, in this moment, might be our only witness to such a crossing in real time. Another layer of intrigue comes from the potential connection between such disturbances and the origin of interstellar turbulence. Turbulence in plasmas is one of the great unsolved problems of astrophysics. How it starts, how it propagates, and how it dissipates remain only partly understood. If the phenomenon Voyager 1 is detecting turns out to be a form of large-scale turbulence, it could offer a unique laboratory for studying these processes. Unlike in planetary magnetospheres or the solar wind where local conditions dominate, interstellar turbulence operates over vast expanses and is influenced by multiple stellar sources simultaneously. In practical terms, this knowledge could have implications for future spacecraft navigation. Turbulent plasma can affect the propagation of radio signals, introduce unexpected electrical currents, and even create subtle drag effects on spacecraft. Understanding the conditions that give rise to such turbulence could help engineers design systems that remain stable and reliable over multi-decade journeys. The notion that Voyager the 1st of May have entered such a region also fuels speculation about what lies ahead along its trajectory. Spacecraft in interstellar space will inevitably encounter regions of varying density and magnetic structure. Some might be relatively calm, others more active. Mapping these differences over time could allow scientists to build a three-dimensional model of the local interstellar environment, much as oceanographers map currents and eddies in Earth's seas. Voyager 1's readings may be one of the first entries in that map, a marker noting, "Here be storms." What makes the current moment so compelling is that this is not the result of a targeted mission designed for this purpose. Voyager 1's original goal was to explore the outer planets, a task it completed decades ago. Its interstellar mission was an extension, made possible by the resilience of its systems and the foresight of mission planners who kept its scientific capabilities alive. The fact that such a groundbreaking detection has occurred so late in its life underscores the value of keeping exploratory missions active for as long as possible. The event also has a deeply human dimension. The faint signal carrying this discovery was received by people who have spent their careers tending to a spacecraft they will never touch again, located farther away than any other human creation. For them, every byte of data is a message from a trusted traveler, one that has weathered unimaginable distances to deliver its story. The bond between human operators and their robotic emissaries is one of the quieter but more profound aspects of space exploration. It is tempting to imagine what could be learned if a new generation of interstellar probes were launched with the specific goal of exploring such phenomena. With modern instrumentation, a spacecraft could carry high-resolution plasma sensors, magnetometers with greater sensitivity, and even telescopes capable of imaging the local interstellar environment indirectly through its interaction with cosmic background light. Such missions could systematically investigate whether Voyager 1's detection is an outlier or a part of a larger pattern that extends throughout the galaxy. This detection also connects to the study of astrobiology in unexpected ways. The interstellar medium is the raw material from which stars and planets are made. Its properties influence the chemistry of the clouds that collapse to form new systems. If plasma disturbances of this scale are common, they could play a role in mixing and redistributing the elements necessary for life, such as carbon, nitrogen, and oxygen. In this way, understanding the behavior of interstellar plasma is not just a matter of physics, but also of tracing the cosmic pathways that lead to habitable worlds. And so, Voyager 1 continues its steady flight, a tiny point of metal and circuitry carrying human curiosity deeper into the galaxy. The latest data it has returned is more than a scientific anomaly. It is an invitation to look outward with fresh eyes, to reconsider the nature of the space between the stars, and to accept that the frontier is not fixed but endlessly unfolding. Somewhere ahead, beyond the range of our current theories, there are more discoveries waiting, and perhaps they will be as unexpected and transformative as this one. The readings that prompted such intense scientific interest arrived in the form of subtle variations in frequency and amplitude, encoded in Voyager 1's long-distance transmissions. To an untrained observer, they might have seemed like little more than static against the silence of space. But to the teams monitoring them, they carried the unmistakable signature of an environment in flux. This was not the first time Voyager had registered plasma waves, yet the duration, scale, and nature of this event stood apart. The spacecraft was not catching a passing tremor. It appeared to be sailing through an active, persistent region of interstellar space, where invisible forces worked ceaselessly on the thin veil of particles that fill the galaxy. Because the interstellar medium is so faint, most of its large-scale structure has been inferred indirectly, using light from distant stars and radio emissions from energetic sources. Voyager's advantage lies in its ability to measure local conditions directly, giving scientists a rare and unblended perspective. The plasma oscillations it detected point to an intricate interplay between particle density, energy flow, and possibly even large-scale magnetic field distortions. Each factor could be contributing to a resonance that keeps the waves going far longer than any transient event should. One line of investigation focuses on the possibility of interstellar plasma highways, extended channels where particle flows are concentrated along magnetic field lines. If Voyager 1 has entered such a channel, it could be experiencing a constant supply of energy feeding the oscillations. These channels might stretch across dozens or even hundreds of light years, linking regions of the galaxy in ways not yet mapped. The physics of such structures would be unlike anything in the relatively small-scale magnetic configurations inside the heliosphere, hinting at a richness in galactic topology that is only now being glimpsed. Another avenue of thought involves the role of interstellar shocks created when different stellar wind regions collide. Stars like our Sun emit streams of charged particles, but massive young stars can generate winds thousands of times more powerful. When the edges of these winds meet, they can create vast turbulent zones. Over millennia, these zones expand and interact, leaving behind shells of compressed plasma that drift through the galaxy. Voyager's readings might suggest it has reached one such shell, a relic of long-past stellar activity, still imprinted on the fabric of space. In some theoretical models, these compressed shells can act as cosmic accelerators. As charged particles bounce back and forth across their boundaries, they gain energy in a process similar to how surfers pick up speed riding ocean waves. Detecting evidence of such a structure firsthand could provide critical data for understanding how the galaxy's population of high-energy particles is replenished and sustained. From a practical standpoint, the discovery opens discussions about how spacecraft instruments can be used in ways never envisioned during their design. Voyager 1's sensors were built for planetary encounters, yet their sensitivity has proven sufficient to detect phenomena at the very limits of interstellar space. This adaptability suggests that future probes might be equipped with multi-purpose instruments capable of functioning across multiple mission phases, planetary flybys, heliospheric studies, and deep space exploration, without requiring major reconfiguration. It also underscores the importance of long-term operational planning. Had Voyager 1 been shut down shortly after leaving the planets, these latest observations would never have been made. The event demonstrates that the further a probe travels, the more likely it is to encounter phenomena we cannot currently predict, making a strong case for maintaining active communication with spacecraft for as long as technically possible. If you like this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on Voyager 1's new impossible discovery after decades in space? We want to hear from you. Thank you for watching and see you next time.